The universe is expanding. This is not a new fact. Edwin Hubble confirmed it in 1929 by measuring the redshift of distant galaxies, the stretching of light wavelengths that occurs when a source moves away from an observer. Every galaxy beyond our local group is moving away from us. The further away it is, the faster it recedes. This alone would be unremarkable. An explosion expands. Things thrown outward slow down over time as gravity pulls them back. The reasonable expectation in 1929 was that the universe's expansion was decelerating, that gravity, operating across cosmic scales, would eventually slow it, stop it, and possibly reverse it into a big crunch. In 1998, two independent research teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, published results that ended that expectation permanently. The expansion is not slowing down. It is accelerating. The universe is not coasting toward a stop. It is speeding up. Something is pushing space itself outward at an increasing rate. Something that has no agreed-upon explanation, no identified mechanism, and no representation in any complete physical theory. We have named it dark energy. It constitutes approximately 68% of the total energy content of the universe. The teams that discovered it received the Nobel Prize in Physics in 2011. The citation described the discovery as having shaken cosmology to its foundations. That is accurate. What follows is what it means. First, a clarification that changes how the problem should be understood. When we say the universe is expanding faster than light, we are not describing objects moving through space at superluminal speeds. Nothing moves through space faster than light. That limit holds. Einstein's relativity is not being violated. What is expanding faster than light is space itself. The distinction is not semantic. Space is not a fixed container that objects move within. Space is a fabric, a geometric structure that can stretch, curve, compress, and expand. When space expands, the distance between objects increases not because the objects are moving through space, but because the space between them is growing. There is no speed limit on the expansion of space. General relativity permits space to expand at any rate, and at sufficient distances, the expansion of space between us and a distant galaxy can exceed the speed of light, meaning the light that galaxy emits will never reach us, because the space between us is growing faster than the light can cross it. This boundary, the distance beyond which light can never reach us regardless of how long we wait, is called the cosmological event horizon. It currently sits at approximately 16 billion light-years from Earth. Everything beyond that horizon is already gone. Not destroyed, not absent, simply beyond permanent reach. The light it is emitting right now will never arrive. The information it contains will never be accessible to any observer in our region of space. The observable universe is already smaller than the total universe, and it is getting smaller every day. Here is what that means in practical terms, or what would be practical terms if the timescales were not so extreme. The Andromeda Galaxy is approaching us. It will collide with the Milky Way in approximately 4.5 billion years, a merger that will produce a new elliptical galaxy over the course of hundreds of millions of years. This collision is gravitationally inevitable because Andromeda is part of our local group, bound to us by gravity strong enough to overcome the expansion of space at this scale. Beyond the local group, every galaxy is receding. The Virgo cluster, the nearest major galaxy cluster, is currently moving away from us at approximately 1,200 kilometers per second. The expansion of space is already winning at that scale. In approximately 100 billion years, roughly 7 times the current age of the universe, The expansion will have carried every galaxy outside our local group beyond the cosmological event horizon. They will not have moved. Space will have grown between us until their light can no longer reach us. An observer in the Milky Way at that time, assuming anything capable of observation still exists, will look at the sky and see nothing beyond their local group. Not darkness where galaxies used to be, simply nothing. No evidence that other galaxies ever existed. The cosmic microwave background, the afterglow of the Big Bang that we use today to reconstruct the early universe, will have redshifted beyond detectability. The universe will look, from the inside, like a small island of matter surrounded by infinite emptiness. The evidence for the Big Bang, for cosmic expansion, for dark energy, all of it will be gone. Not disproven, simply no longer accessible. An observer with no knowledge of what came before would have no way of knowing the universe they inhabit was once filled with 2 trillion galaxies. A 2007 paper by Krauss and Scherer in General Relativity and Gravitation examined this scenario in detail. Their conclusion was that future civilizations, if any exist at that epoch, would be unable to reconstruct modern cosmology from available data. The universe will have erased the evidence of its own history. Now let's follow the timeline further. Beyond the isolation of the local group, the stars begin to die. Stars form from gas clouds, primarily hydrogen, the most abundant element in the universe. As stars burn, they convert hydrogen into heavier elements and disperse them through supernova explosions. The dispersed material can, under the right conditions, collapse into new stars. But the supply of hydrogen is finite. The universe is not creating new hydrogen. What existed after the Big Bang is what exists now, minus what has been fused into heavier elements and locked inside stellar remnants, white dwarfs, neutron stars, black holes. The rate of star formation has already been declining for approximately 10 billion years. We are past the peak. The universe is in the long twilight of its stellar era. In approximately 1 trillion years, the last stars will exhaust their fuel and die. Not all at once. The smallest red dwarf stars burn so slowly that they can persist for 10 trillion years. But eventually, the last one will cool and darken. What remains at that point is a universe of stellar corpses, white dwarfs cooling over incomprehensible timescales, neutron stars. Black holes of varying sizes, from stellar mass to the supermassive black holes at the centers of galaxies, which by this point will have consumed most of the matter in their vicinity. The universe will be dark, not metaphorically, literally. No stars, no light sources. A vast, cold space filled with objects that no longer emit anything detectable at distances beyond their immediate vicinity. The black holes are next. Black holes are not permanent. Stephen Hawking demonstrated in 1974 that quantum mechanical effects near the event horizon cause black holes to slowly radiate energy, a process now called Hawking radiation. The rate of radiation is inversely proportional to the black hole's mass. Small black holes radiate quickly and evaporate in seconds. Supermassive black holes, the ones at the centers of galaxies, with masses billions of times that of the Sun, radiate so slowly that their evaporation timescale exceeds the current age of the universe by many orders of magnitude. But they do evaporate, given enough time. The largest black holes in the observable universe will fully evaporate in approximately 10 to the power of 100 years. This number, a googol, is not meaningfully comprehensible. It exceeds the number of atoms in the observable universe by an incomprehensible margin. And yet, it is finite. Given enough time, the last black hole evaporates. Its mass is converted entirely to radiation, photons and other particles dispersed into an increasingly cold and empty space. After this point, the universe contains no significant concentrations of matter, No stars, no planets, no black holes. Photons of ever-decreasing energy drifting through space that continues to expand. A universe in which the temperature approaches but never quite reaches absolute zero. This is the heat death. Not an explosion, not a collapse. A gradual, unstoppable approach toward maximum entropy. A state of perfect thermodynamic equilibrium in which no energy gradients exist, no work can be done, no information can be processed. A state in which nothing happens. Not because something prevents it, because there is nothing left that could happen. There is a detail in this timeline that is rarely discussed outside of technical literature. The protons in ordinary matter may not be stable. The Standard Model predicts that protons are stable, that a proton, left alone, will remain a proton indefinitely. But several extensions of the Standard Model, including grand unified theories, predict that protons decay with a half-life somewhere between 10 to the 34th and 10 to the 36th years. No proton decay has ever been observed. The Super Kamiokande detector in Japan has been monitoring a 50,000-ton volume of purified water since 1996, watching for the signature of proton decay. As of current data, the lower bound on proton lifetime is approximately 1.6 times 10 to the 34th years. If protons decay, and the theoretical argument suggests they should, then ordinary matter itself is temporary. The atoms in your body, the atoms in every planet and star and galaxy are not permanent structures. They are configurations of more fundamental components that will, given sufficient time, dissolve back into radiation. The timescale is so extreme that it makes the heat death timeline look brief by comparison. But the endpoint is the same, a universe in which the last proton has decayed, in which the last stable structure of ordinary matter has dissolved, in which the expansion continues, cold and dark and empty, toward a future in which the concept of structure itself no longer applies. This is what the equations produce when followed to their conclusion. Not metaphor, not poetry. The equations, followed past every horizon we can currently observe, produce a universe that ends not with sound or light or catastrophe, but with the slow exhaustion of every gradient, every structure, every capacity for change. In 1998, two teams of astronomers pointed their telescopes at distant supernovae and expected to measure the deceleration of the universe. They measured the opposite. The Nobel Committee, 13 years later, described their finding as having shaken cosmology to its foundations. That is accurate. What it shook cosmology into was a picture of a universe with a specific and calculable future. A future that is not approximate or theoretical, but is, within the constraints of our current physics, inevitable. The expansion will continue. It will accelerate. The galaxies will recede beyond the horizon. The stars will die. The black holes will evaporate. The protons will decay. The temperature will approach zero. The entropy will approach maximum. And the universe, in the technical thermodynamic sense of the word, will reach equilibrium. Nothing will disturb that equilibrium. There will be nothing left to disturb it. One question. The Krauss and Scherrer paper concluded that future civilizations will be unable to reconstruct modern cosmology because the evidence will no longer be accessible. The expansion will have erased it. We know the evidence exists now. We can see it, we can measure it. We are living at the one moment in the universe's history when the full picture is visible to an observer with the right instruments. Does that change anything about how you think about now? Drop your answer in the comments. Next video, the objects we cannot track. 1 billion dark neutron stars moving through the galaxy at hundreds of kilometers per second. The math behind how close one needs to pass to sterilize Earth, and why we have no warning system for it. See you there.